This module covers chemistry and material properties. So those are two different sections of the FE. So the chemistry right here covers oxidation, reduction, redox reactions, acids and bases, so the pH, and chemical reactions, so being able to like balance stoichiometry, finding equilibrium coefficients, just balance a general reaction, that kind of thing. So this says here 5 to 8 questions. But what I have heard from students who have taken the test is that there is way more chemistry than they expected. So I would say that this is probably going to be closer to 8, if not even higher. There does not seem to be a lot of quality control on the exam from NCES. So chemistry is something that you really want to study, especially because it's probably been so long since you took chemistry, and there is a lot to remember. The handbook does have a periodic table, which is good. You'll definitely need that, but you'll want to look over your notes from when you actually took chemistry class, your cheat sheet for the final or whatever it was that you studied to be able to do well in that section. And then the material science is sort of related to the chemistry. So if we scroll down to that, it is here. So material science or material properties is section 11. So this will cover like phase diagrams, mechanical, chemical, thermal, electrical, material selection, any of this stuff. So like being able to read a phase diagram, being able to identify like when to use or what is a heat capacity, what is a density, and being able to identify those variables in formulas and then solve for whatever it is that it's asking. So this is related to chemistry, but it's more the material science aspect. So let's look next at the handbook. So if we go to the chemistry, so this is chemistry and biology section. It is mostly chemistry. So there should not be any biology on the test. So here we need to know, okay, Avogadro's number given to you, molarity versus molality. So this is grams of moles dissolved in a liter of solution or 100 grams of solvent. The equilibrium constant, be able to find this. So this is what these formula or what these variables represent is A and B would be the reactants. And then that's the capital letters. Concentration of reactant. And then these lowercase ones, these exponents, are going to be their coefficient in the chemical reaction. So looking down here at this chemical reaction, so this ABCD is the same as this ABCD. So you would put the concentration of each product raised to the power of its stoichiometric coefficient here, and then the same thing for the reactants. Those would go in the numerator. And if you have a third reactant or a third product, just go ahead and multiply that in either the denominator or the numerator as appropriate, the same way that these are done. All right, so Faraday's equation, they probably won't really ask you a lot about that, but there may be a lot of concept questions here that you want to know in both the chemistry and the material properties section. So many of these, the words that are in italics, those are things that may show up in a problem, and so you will just control F something like control F. Say you don't remember what a catalyst is. Catalyst expedites a chemical reaction, but you would just say catalyst. Find it. There are only 4 matches, so one of them is here, and then the other one is here. So you will do a lot of control F in this area. So the atomic number is the number of it in the periodic table, and that is also the same as the number of protons in the atomic nucleus, or number of positive charges. Nernst equation, I probably won't ask you about that. Acids, bases, pH, they probably will. So know how to find the pH from the concentration of H+, or vice versa. Bioconversion, okay, so this is probably a little bit more than they're going to ask you, but it is there if you need it. Photosynthesis equation, instrumental methods of analysis, they might ask you this, but probably not. Periodic table, definitely you're going to refer to this. So focusing on here, we take a standard thing in the periodic table. So let's say carbon. So carbon is in column 4 here, which means it has 4 valence electrons. Remember that an atom always wants to get to 8 valence electrons to be full. So a carbon here is going to either want to lose or gain 4. Now, this 6 here is the atomic number, and this says how many protons are in the carbon atom. And then the atomic weight, here being 12, is basically how many protons plus how many neutrons, how many things are in the nucleus. So if you want to figure out how many neutrons are in there, then you take the atomic weight and you subtract the atomic number, and that tells you the number of neutrons. So something like oxygen, this really the most common ones that you're going to have here: hydrogen, sodium, potassium. Those are common ones, maybe lithium, because all of these try to give up an electron because it's easier for them to give up one than to gain 7. Okay, so you would have probably these: hydrogen, lithium, sodium, and potassium. These are good ones to know. And then carbon, nitrogen, oxygen, sulfur, chlorine, fluorine, helium, neon, and argon. So these are the ones that you would want to know. They don't really ask you much about boron, but anything here in groups 4 to 8 and up down here through argon, you want to know those. And here you want to know these. So we have these ones over here. Also, these are going to more try to gain electrons, and the ones over here are going to try to lose electrons. Okay, so rules of organic chemistry. Most people aren't going to take organic chemistry unless they're actually chemical engineers. So this is not really, super applicable. You might need to know these molecular formulas. So if the question asks you something about, say, muriatic acid, and you have no idea what that is, Control F it, and then you'll know the chemical formula or molecular formula here, and then you can actually use it in a balanced reaction equation. So know stuff about batteries. So this electrochemistry is basically battery stuff. So cathode, anode, oxidation, lose electrons; reduction, gain electrons; cation is positive, anion is negative. These are some standard oxidation potentials. So this corrosion reaction, these are all partial corrosion reactions. Pretty much one thing or one element will split up and lose or gain certain electrons. So this is all for lost electrons. So if it's a redox reaction, you'll have to pick 2 of these, combine 2 of these, and make whatever compound it is that it asks you about. Okay, and biology is not going to be on it, so we'll stop there. The material science or material properties section is very similar to chemistry. So looking here, it talks about atomic bonding, corrosion reactions, so anode, cathode, redox reactions, which was also covered in the chemistry section. So you will find similar topics in between the materials questions and the chemistry questions, which might also give the illusion of having extra chemistry on a test. So the diffusion equation here, this is for basically ions diffusing into a substance. So you would follow this formula to find it. And this is related to absolute temperature. So the important thing to note here is that absolute temperature would need to be in Kelvin or Rankine. Don't use Celsius for this, or Fahrenheit. For thermal and mechanical processing, this talks about different types of heat treatment for mostly metals, but you can have thermal processing probably for other materials too, but it's mainly for metals. So this is when you would heat them or cool them to particular temperatures in particular fluids at particular speeds to change their material properties. So cold working is plastically deforming a metal, and quenching is when you drop it in water or oil or something like that in order to prevent the formation of equilibrium phases, which changes the crystal structure. So you can get different types of crystal structures depending on what type of quenching or heat treatment that you do. So electrical properties of metals, this is how to calculate charge, capacitance, resistivity. So this is all related to electrical stuff. And then mechanical properties can also change based on the heat treatment. So you can calculate the strain, which is change in length over the actual length. And then there is a formula for that. You probably won't have to actually do the integral of it, but just the generic formula. There are these charts of material properties here. So this is going to be super useful for problems both here and in the chemistry section. So you've got all of the different types of metals, symbol atomic weight, so that's stuff in the periodic table, but density, melting point, specific heat. So this is amount of heat per kilogram. And then electrical resistivity and conductivity. So electrical resistivity and conductivity are sort of opposites of each other. So something that has a higher resistivity is going to be less conductive. Although electrical and thermal conductivity are different, they are a lot of times similar to each other. So semiconductors probably won't ask much about that. Impurity levels probably don't really need to know that. Okay, engineering stress, force per unit area. That's pretty common, so same units as pressure. And then you can also have key mechanical properties from a tensile test curve. So there might actually be a question on this. Elastic modulus, ductility, ultimate tensile stress, and yield strength. So these are things that you can all get from the tensile test curve, which is that force versus percent elongation, where you get that sort of, looks like almost a first order exponential curve that comes up and plateaus, but then starts to go down a little bit as the metal starts to nick or undergo a, gosh, not exactly like a ductile failure, but like plastic deformation. That's what I meant to say. So creep is time-dependent deformation under load, registered by strain rate. So that's basically like its rate of change of length. And then you can also calculate the fatigue life or fatigue resistance. So a fracture toughness is basically combination of applied stress and crack length. So it is like, when will the material fail? Now we can see here with these two diagrams, you can have an exterior crack or you can have an interior crack. So depending on where the crack forms, if it forms on the outside edge, then it has to propagate all the way across. If it forms on the inside edge, it'll propagate in both directions. So those inside cracks are harder to find and can be a little bit more dangerous. Relationship between hardness and tensile strength, AST and grain size. Probably won't need to know a whole lot about that. Composite materials, not a whole lot there, but metals would be the main thing to focus on. So hardness is resistance to penetration. So there will definitely be some questions that ask you to read charts. So with this chart, the hardenability curve shows you is how the hardness changes with the distance from the end if you have a rod that was quenched on one end of it. So this tells you like it is harder when it is close to the quenched end, and then the hardness decreases as you get further from the end. And these are different types of metals. All right. Okay, so bars that are quenched in agitated water. So this circle is the cross section of a bar. So C is the center, S is the surface, and then this M minus R and R are just different points in between. So if we look at these two different curves, this top curve or top graph here is for quenching in water. The bottom curve is for quenching in oil. So we can see here the x-axis is distance from the quenched end, and the y-axis is the bar diameter. So if you wanted to know the property at each curve, or the cooling curve for each of these things. We can see here the center is going to be the slowest to cool, and then the surface will be the fastest to cool, and they follow these particular curves based on the bar diameter and the distance from the quenched in. You can tell its cooling rate. And same thing here for oil. The curves just follow a little bit different pattern. Sharpie impact test. This is very, very common, used to find the energy required to fractal, and you can identify the ductile to brittle transition. So this is the temperature, basically the amount of energy versus the temperature. You can see when it is a high energy fracture versus a low energy fracture. And obviously it is going to take more energy to fracture at a higher temperature because it is more ductile at a higher temperature, whereas it will be easy to shatter if it is extremely cold because it'll essentially be frozen. Like if you think about it, you can break ice a lot more easily than you can like break water because water just comes right back together. Concrete might ask you some questions about concrete. So what this graph shows is how concrete strength changes based on the water cement ratio with and without air mixed inside of it. So mixing concrete at different with different ratios of water to air and solid changes the strength rate. The age here is also, this is also for concrete. So we have age of the concrete in days and then the compressive strength. So concrete is one of those things that sort of has to cure to get stronger. So right when you first pour the concrete, it is liquid essentially, so it's not very strong. But as it cures, then, so here we can see after like 90 days, then this is pretty flat, but you can see all of the different conditions. Some of them flatten out, whether it, if it's in a laboratory, if it's in the air, and different locations of the cooling and then how long it lasts will affect the compressive strength. Concrete is really strong in compression. It is not that strong in tension, so that's why we put rebar on it. The point of the rebar in the concrete is to induce a compressive force on that concrete so that it will not crack as easily if it is subjected to an external force or a tension load, because any tension that's applied to the concrete would have to first undo the compressive force from the rebar, and then also the rebar can hold the tension. So that's why you put rebar in concrete. It makes it stronger. So amorphous materials, these are non-crystalline materials. So like glass would have not really a crystal structure. A thermoplastic polymer is just sort of semi-crystalline. So it has some crystals, but not great. So this is showing temperature versus volume. So basically these curves here, this point between the glass and the liquid is where glass sort of becomes a liquid. And it's interesting that glass is almost, because it doesn't have a fully crystalline structure, then it can change its shape over time even when it's a solid. So if you look at windows in really old houses, they'll be thicker at the bottom than at the top because of slowly over all of those years, the molecules of the glass are sinking. Now, a polymer is basically a plastic. So that's something that can be melted and remade. And we can see that the temperature does not really follow a straight line at all. And polymers are, because they're plastic, fail under ductile failure by necking. You can add things to polymers to improve their properties for commercial use. Similarly to a composite, you would throw some type of filler in it, and that would change its properties and make it desirable in some respect. Thermal expansion coefficient is the ratio of the strain to the change in temperature. So if something grows and shrinks a lot based on temperature change, that has a high thermal expansion coefficient. If it doesn't, then it would have a low thermal expansion coefficient. So this just talks about specific heat capacity. So specific heat is like this is heat per unit of mass, and then the heat capacity is based on the moles and not the mass. So phase diagrams, there will probably be a question on phase diagrams here. So this shows different phases of a material based on its composition and its temperature. So if you have certain types of chemical reactions or like heat treatment reactions of a material will cause different types of phases. So these are just the different kinds of reactions in what sort of phases that they would go to, and sort of, the back and forth here. So alpha, beta, and L would be three totally different phases. So L is the liquid phase, and alpha and beta are the two different types of solid phases. So this is just showing, you might get all liquid, you might get solid and liquid, you might get two different types of solid compositions. These are just things that will happen based on the composition and the temperature. So this one is an iron and iron carbide phase diagram. So iron is Fe and iron carbide has carbon in it as well as the Fe. So by weight percent of carbon, then you can track that on the x-axis, and then you could track the temperature, Celsius or Fahrenheit, on the y-axis. And this also shows the different types of phases that would occur. So you could have liquid, you could have an alpha, a gamma, or a delta, different phases. Let's take a look at the D2L. And there are two review videos here. So there is this chemistry review video. This has examples of 5 different types of chemistry questions. You will probably get a lot more chemistry questions than that on that FE. So I would also recommend studying from your notes of when you took chemistry or your cheat sheet for that. The material properties review, this has examples and kind of shows the handbook. So take your quiz. You can have 2 chances to take this one. So once you take it, figure out where you went wrong, do the correct that and take it again. Then for the real quiz, you get 1 chance, but you can also do corrections on that to get half credit back. And finishing that will unlock the next module, which is ethics and safety.